In Thermochemistry 2, we're looking at enthalpy. Before we can look at enthalpy, we need to review a few things about internal energy. Now, you should remember from the previous section that internal energy was the total potential and kinetic energy. However, now we get to discuss the fact that we have no way of knowing this. So, what we do know is that Q and W played a role. However, how Q and W change is irrelevant. In other words, the path of change doesn't matter. What matters is simply the overall change. In other words, the total change that we have that occurs based on the initial versus the final condition. The example here, obviously, ice warmed up, hot water cooled off to 25 degrees Celsius. This is the current state. That's what matters. In other words, if you look at a battery, if the battery either loses its charge by sitting on the shelf or loses its charge by being used, the Q and W are different, but the total change in energy is the same. This is why it's known as a state function. This matters because this is what ultimately impacts enthalpy. So let's look at the relationship between enthalpy and internal energy. Since we can't look at the total internal energy if it's too complicated, we have to find a way to look at changes in energy, and this is where enthalpy comes in. Notice the relationship is internal energy and pressure volume work is what determines our enthalpy. Now, one of the things to look at here is oftentimes pressure volume work is very, very small. In fact, it's almost considered negligible. So our enthalpy and our internal energy differences are typically very, very small. So they're almost equal. This is why enthalpy will work. So now let's look at the derivation. If I change enthalpy, that means the change in enthalpy is the result of a change in internal energy, a change in pressure volume work. Remember from the previous section that we know the internal energy is Q and W, our heat and our work. We also know that work can be determined by pressure volume changes in a gas. If I substitute these in, lo and behold, this is what matters right here. Our delta H is equal to Q. In other words, the heat change becomes equal to our enthalpy change. Now, the caveat, constant pressure. As we move on, there will be times when the pressure is not constant, but for now, we deal with it as though it is constant. The importance of this is what it means in terms of calculating the enthalpy of a reaction. In other words, just like with enthalpy, where I had final minus initial, that's exactly the same thing going on here. Now, a point to remember that you've already seen in other places is notice the values, notice the positive versus the negative. In other words, the direction I'm going determines and is important to the amount of energy, whether energy is absorbed or released. Notice that the total change is identical. It simply matters whether I am going from carbon dioxide and water to methane and oxygen, or methane, oxygen to carbon dioxide and water. So that means that there are a few things we do know. Enthalpy is an extensive property, so it depends on mass, whereas an intensive property is basically a ratio, like kilojoules per mole. So our enthalpy associated with a particular substance is constant. I'm going to release this much energy per mole, but the total amount of energy depends on how much I have, and this is what is our difference between intensive and extensive. Now, as we already noticed in the previous section here, this is positive and negative. We know that opposite sign, reverse reaction, our enthalpy change is going to be the same in both directions. It's just a difference of whether energy is absorbed or energy is released, and the state of the products and reactants matters. This is partly going back to the state function. This also has to do with something we'll be talking about in a little bit, which is heat of formation. So, why we care, this leads us to Hess's law. Hess's law is what actually allows us to determine and compare the reactants and the products, that idea of initial and final in terms of determining an overall heat of reaction. Think of it as Hess's law of summation. I'm not even sure if summation is the right word, but in essence, what we do is we sum or look at the total heats of enthalpies changes associated with various substances and compounds, and we can actually add them up, and that will give us our net change. So when we look at something like what we just saw with our methane and our oxygen and our CO2 and our H2O. In other words, what we do is we can imagine this being carried out in a series of steps. We utilize what are known as known values, predicted values, and we can use those to determine an overall change, what the net change is. And by looking at it in parts and pieces, we can actually add equations together, kind of like in algebra or sort of what we did in net ionic equations. So again, the point is that we don't care about the way it's changed. In other words, the path is irrelevant. We simply care about the total change. And that total change is always the result of the reactants and the products. Okay? So that initial and final, the reactants and products, and so we can compare and set it up just like what we saw with heats with the internal energy, where I have enthalpies associated with the products minus the enthalpies associated with the reactants. But there is a catch. We can't just use random enthalpies, we actually have to use something known, and this is where enthalpies of formation come in. The point about enthalpies of formation is it's associated with the energy change when I use an element to form a particular substance. So in your book you have a similar table. There's also an appendix in the back. The point here is to notice that when I look at something like calcium carbonate, that's literally the formation of calcium from carbon, oxygen, and its constituent elements. Now in truth, we don't really see the formation this way, but it's an effective way of measuring our heat of formation. And just a little side note here, standard conditions. Notice the difference between standard conditions and STP, and the difference here is the temperature. And this is something that's probably good for you to just kind of keep in the back of your mind. STP, 0 degrees Celsius, 1 atmosphere, standard conditions, 25 degrees Celsius. So the point is, if I know these, I can look at a net equation, okay, propane producing CO2 and H2O, and I can actually break it down into steps. And the advantage of breaking it down into steps is it allows me to actually look at and determine my enthalpy changes at each place along the way. This is the power of Hess's law. So I'm going to combine these into one equation. So notice I've taken all of my reactants and I've put them together, and I've taken all my products and put them together. And so we see a situation very similar to what we saw with net ionic equations. We have some things that are the same on both sides. So I have 3C on both sides, I have 4H2 on both sides, and then I have 3O2 and 2O2 for a total of 5O2. And so notice what I now have is I have my actual equation above after looking at it in terms of heats of formation from constituent elements. Now the other point here is notice how these equations were arranged. In other words, when we looked back at our heats of formation, it was forming products from the constituent elements. So notice that I've actually put this one on the left as though it's going to break down and form carbon and hydrogen. And I've set these up so that my CO2 is on the right and my H2O is on the right, exactly where I need them in my final equation. This is also what Hess's law allows us to do, is to manipulate known equations so that we can produce a new equation to determine a new heat of reaction for something that we may not know because we don't necessarily measure it. If we can measure it directly and compare this, then we can kind of verify what we know. Ultimately, the point here being that I can manipulate these to do this. Also notice that I have multiplied. Okay, so when we look at, for example, here, plus 103, and CO2 is suddenly 1181. It's actually negative 1181. This is different from the chart. In our heat of formation chart here, carbon dioxide, negative 393.5. So to get negative 383.5 to this number, I have to account for the molar amounts, because again, remember in the chart, it was kilojoules per mole. So if it was kilojoules per mole, I suddenly have 3 moles, so 3 times 383 is going to give me this 1181. Also notice they did the same thing for the water. It's a negative 1143. and water is negative 285.8. Now, in putting this together, we basically are comparing our products with our reactants. Remember, for math, this means the sum of, so we're putting everything together. And when I combine that, notice here they show you the multiplication that they did to determine these. And when I put it all together, I end up with an overall heat of reaction associated with this equation. And notice that my heat of reaction here is per mole of propane. So if I reverse this and I say CO2 and H2O is going to form propane and oxygen, then it would require 2,219.9 kilojoules of energy. So let's look at a quick example. If I have P4O6 plus O2 yielding P4O10, these are my known heats of formation. So I need to rearrange these to create this equation. Notice that my P4O10 is on the right, here P4O10 is on the right. So I want to leave this equation exactly as it is. However, the other side, I need to get rid of this P4. I also need the P4O6 to be on the reactant side. So I'm literally going to reverse this equation. Now, when I reverse this equation, I have to remember to reverse my enthalpy. So now, when I put these together, we can look and see our P4s are going to cancel. I have 5 O2s to 3 O2s, so I'm going to be left with 2 over here. So I have the equation, the exact equation I want, just as above, and when I total these together, I end up with negative 1,300. This is Hess's law. This is all that we do with Hess's law. It's just this ability to sum all of these different things together. Where we see things like this applied are when we look at energy of foods or when we look at energy in fuel. Now, 3 more final points before we end. You must be able to do graphical representations of reactants and products and the energy changes. That is, in essence, you should be able to show some kind of net change in energy associated with where I start in terms of reactants and products, whether it look like this one where you show the used energy to break the bonds and the releasing of energy as I form bonds, or simply a net change. Either way, you have to be able to do the graphical representation. You also have to be able to utilize heats of formation to determine the heats of reaction. And that's what we did in our practice problem. So you have to be able to utilize that information to solve problems. And now we get to start putting it together with previous information and our whole idea of heating and cooling curves. So that means that I can take the heat of vaporization, which was an enthalpy, the heat of fusion, which was an enthalpy, and I can utilize all of that information together along with Q associated with the change of temperature of something, and I can start looking and computing and doing everything associated with heating and cooling curves.